A high-output Y-source boost DC/DC converter for renewable applications. Boost DC/DC converter based on Y-source impedance network with high gain without and with closed-loop control is analyzed in this paper, which provides solutions to distributed generation applications. The analyzed converter consists of a Y-source impedance network which has 3-winding inductor tightly coupled for high voltage boosting, which is indeed higher than the other classical impedance networks. Turns ratio and winding placement of this inductor can be designed to give the gain desired, while maintaining the duty ratio of switch smaller. Principle of operation is presented and analyzed by mathematical derivations and calculations. Analyzed converter is simulated using MATLAB and the results are in agreement with theoretical analysis and confirm the performance of analyzed converter. Keywords: DC/DC converter, Y-source, impedance network, closed-loop control, pi controller. Introduction. Distributed generation powered by renewable energy sources like solar and fuel cells etc. have been gradually recognized as the reliable way of providing premium power for meeting energy demand in future for a low cost. Realizing such a distributed grid however requires more demanding power electronic converters for enhancing the low source voltages to a predefined grid voltage. Consider fuel cells as an example. Their power densities are comparably high, which along with their low emission and quiet operation, make them attractive as distributed sources. However, the output DC voltages are low usually, and vary widely. Converters with high voltage gains are thus needed generally for tying fuel cells to the distributed grid. Their ranges of gain variation must even be wide for tracking the wide output voltage variations of fuel cells. It is hence important to style high-gain converters for these sources, whose gains should ideally nullify the source variations before a regulated voltage are often obtained for grid interfacing. The converters that are designed should also match with other requirements of the intended sources, which for solar and fuel cells, are to avoid negative currents flowing into them and limit ripple currents drawn from them too. The converter types can be DC/DC, AC/AC, AC/DC or DC/AC depending upon the system requirement. For DC/DC converters, conventional boost 3, push-pull 4, half-bridge 5, full bridge 6 and those with numerous voltage multiplier cells 7 have been tried for boosting low source voltages to a regulated DC link voltage between 200V and 600V depending upon the system requirements. The amount of boosting voltage demands the inclusion of high-frequency transformers in the converter circuits, whose turns ratios are increased proportionally with the demanded gains in almost all cases. The resulting turns ratios and total number of turns might therefore be high if high gain and satisfactory coupling are to be ensured simultaneously. 6-8. Alternatively, cascaded or multilevel techniques can be introduced to the converters for raising their gains, but the number of components and complexity involved will undoubtedly increase. Another way is to use 2-winding coupled inductors for boosting voltage, whose turns ratios can be kept low comparably even at high gain voltage. Converters which are implemented with coupled inductors therefore can have higher power densities, as compared to the earlier mentioned methods. The coupled inductors are different from the high-frequency transformers earlier mentioned since their magnetizing inductances are designed intentionally to be finite, ideally infinite for transformers. Based on this, a few magnetically coupled impedance networks have been found, whose origin dated back to the Z-source impedance network introduced in 9. The Z-source network and its subsequent quasi-1011, embedded 1213 and series 14 variations use 2 inductors and 2 capacitors for voltage boosting. They have been demonstrated for DC/AC inverter 22, DC/DC converter 23, AC/AC converter 24 and AC/DC converter 25, but their gains are mentioned to be low. That has led to the development of the switched inductor 15, tapped inductor 16, cascaded 17, T-source 18, trans-Z-source 19, and T-Z-source 20 networks. The latter 3 networks are considered different from the others since they use magnetically coupled inductors for boosting gain. They are also different from those push-pull and bridge-based converters mentioned above in the way that their gains are increased at a rate faster than the usual proportional relationship with turns ratios. Their turns ratios and total number of turns can therefore be comparably lesser, while retaining the necessary magnetic coupling at higher power density. It is hence the intention of this paper to continue by analyzing a Y-source network implemented as a high-boost DC/DC converter 21. The resulted converter uses a 3-winding coupled inductor for flexibly deciding on its gain, which is presently not matched by any related converters. The number of components used is also kept small to allow the converter to be implemented compactly without compromising its performance. Y-source boost DC/DC converter without closed loop consists some error in the transient state. To reduce this error, closed loop controller is used. Results thus obtained are in match with theoretical analysis and confirm the performance expected from the converter. Y-source impedance network. It consists of an active switch SW, a passive diode D1, a capacitor C1 and a 3-winding coupled inductor, N1, N2, N3, for the high boost at a small duty ratio for switch SW. As the windings of the coupled inductor are connected directly to switch SW and diode D1, its coupling should be tight to ensure very small leakage inductances at its winding terminals. For the Y-source inductor, 3 strings are wound to form 3 coupled windings inductor. Principle of operation. The Y-source boost DC/DC converter is as shown in Fig 4, where only one controllable switch is used. In addition to the basic Y-source impedance network shown in Fig 1, there is an extra diode D2 and capacitor C2 across load. Now, when the switch SW is turned on, diodes D1 and D2 will reverse bias simultaneously. Then C1 to charge the magnetizing inductance of the coupled inductor, and C2 to power the load. Turning SW off, on the other hand, causes D1 to conduct, and the input source to recharge C1. The input source, together with the coupled inductor, also supplies energy to recharge C2 and power the load, but only if the voltage VO across capacitor C2 is lower than voltage across switch SW. Then D2 conducts, hence linking C2 and the load to the rest of the circuit. The same is repeated when SW turns on again. By periodically switching SW, the load voltage VO across C2 can be regulated, which according to equation 5, represents a gain of. This is the maximum gain that the Y-source network can provide. B. Expected operating waveforms. Based on the operating principle described above, Fig 5 shows some expected waveforms from the Y-source boost DC/DC converter in response to the applied gate source voltage VGS to switch SW. When SW is on from T0 to T1, .dst equals T1 T0/Ts, its drain source voltage VDS falls to 0, while its current IDS increases to a finite value. That causes diodes D1 and D2 to become reverse biased, and their voltages VD1 and VD2 to increase. The input current N, which is also same as the current ID1 through D1, then collapses to 0 during this interval. When SW turns off at T1, VDS across it increases sharply, together with N equals ID1 and ID2 through the two diodes D1 and D2. These currents, in turn, charge capacitor C1 and C2 with voltage across C2 increasing slightly above voltage across switch VSW at T2. When that happens, diode D2 stops conducting with current across diode D2, ID2 return to 0. Since ID2 comes from the DC source, its reduction to 0 also causes N to drop. The converter remains in this state until SW turns on again at T3. Ts equals T3 T0, causing the waveforms to repeat the patterns. For N and ID2, it should be mentioned that their patterns can change depending on the charging time constant of C2. Longer charging time will increase the interval between T1 and T2, while a shorter charging time will reduce it. This variation however will not affect the maximum gain that is produced by the converter.